I'm going to talk to you about the component parts of a robotic system. So one of the first things that you'll see when you see a robot is its mechanical structure. So we're going to be considering mainly arm mechanisms in this particular module. And if you consider what a robotic arm looks like, it's not that unlike, in many cases, what a human arm looks like. So it's composed of these links, which basically have joints at each end. And the idea is to have a mechanical structure which can then basically support the task you're doing. It's got, obviously, you've got to have the structures in order to get this thing to move in a certain way. And the actual structure itself is going to have dynamical properties, so it's going to take force to actually move it. And it's also got to be structurally strong actually to perform the task that we're asking of it. Now, the arm on its own would be of no use unless it was actually driven somehow, and that's what actuators are for. We need some kind of means of generating torques at joints, and this could be done, in this case, with a stepper motor. It could also be done with DC motors. But there's also other technologies as well, and in larger robots you might even get hydraulic drive, and in other applications you might get pneumatic drive. So you're using fluid power in order to get these things to move around. Now, just like humans, if we're doing a task, we're watching what we're doing and we're also feeling what we're doing. A robotic system also needs to sense what's going on, and generally we'll build sensors into the system. So if we're just thinking in terms of the arm and noticing where it is, for example, we might just put something on each joint to measure the angle. And an example of that might be an incremental encoder. Many tasks these days, or many systems these days, of course, are run using computer control. It is possible sometimes to do specialist hardware just for the particular task, but generally speaking, we're going to be using a computer or a microcontroller in order to actually control these things. And also these then interface to things like power amplifiers to drive the actuators, and input signal conditioning to read what the sensors are doing. So there's many different structures of arms. For example, I'm just showing you three here. Here's a Revolute arm, which is a very common design. The Scara design, which is very good for pick and place. And also this parallel delta kind of robot design, which is actually very good for very high speed operation. There's lots of different designs out there for different kinds of arms. Again, we'll be concentrating on what we call a serial set of linkages, and by what I mean by that is, basically everything goes following one sort of path. So we've got the base, the lower arm and the upper arm as a sort of a series of links. The same for this Scara design. We've got the base, we've got the first arm part here and the second arm part here. So in this particular course, we won't be looking at things which actually use parallel arm mechanisms, although it's quite easy to extend what we're doing here in this course to understanding how these things work as well. Well, now, really one of the main aspects of understanding robots is knowing where the endpoint of the robot is, where let's say we've got the tool, we want to know where that is in terms of where the base is. So if you're doing a task, you've got to get the robot to move to a certain place. So what we care about in the first instance is how can we work out where the endpoint is relative to the base of the robot. And this is going to be affected by how the thing is configured, how the joints set in the robot, because as you change the joints, you change the endpoint. Now, if you know all the dimensions of the arm and you know all the angles of the joints, you can calculate where the endpoint is, and this is called forward kinematics. Right? So given the angles, given the configuration, we can work out where the endpoint is. Now, for lots of tasks, that's not what we want, right? For lots of tasks, we know where we want the endpoint to be, but we don't necessarily immediately know what the angle should be. So working out what the angle should be from where we want the position to be is known as inverse kinematics, because it goes the other way round, right? So just to summarize, forward kinematics, we give it the joint angles if it's a robot like this, and we want to know where the endpoint is. And in inverse kinematics, we know where we want the endpoint to be, and then we need to calculate where the joint angles actually need to be as well to get it to that place. right? So how do we get these robots to move? Well, there's lots of different kinds of actuator technologies out there. Probably the most up-and-coming one is a brushless motor, right? A brushless DC motor, and this is a magnetic device. We pass a current through some stator coils, and this interacts with the magnetic field on, let's say, a permanent magnet, and it causes it to rotate. And we use electronic commutation to make sure that we're always switching the current appropriately, so it always goes in the direction we want it to do, to go in. And these things can generate substantial torques, but not usually enough directly to drive a robot arm. And so typically we will need some kind of gearbox, which is unfortunate, but it's just because the torque is just normally not high enough on its own. These brushless motors, however, are normally very reliable. They last a very long time, and I would say, you know, if you've got the opportunity in a high-end design, that's kind of the technology you should be using to build robotic arms. Slightly bit more old-fashioned is the brushed DC motor. So, as you probably all know, in order to get a motor to actually rotate, you do need to keep switching the direction of the current flow through the coils, otherwise it wouldn't rotate. And in a brushed motor, this is done using a mechanical switch, which is typically built up from a commutator with brushes pushing against it, and as it rotates, it automatically switches appropriately. So these things obviously, you know, are going to be a bit cheaper than the brushless motors, but they are very, very effective. But just like the same, well, basically the same kind of principles apply as well in terms of torque. Generally, we can't use it without a gearbox because we can't use it directly, but they're very, very useful things to use for cheap projects. Another thing which is particularly useful for kind of hobby projects or proof of concept projects is the RC servo. So these are little tiny servo systems. You tell it where you want the thing to be positioned and it will go there. These are driven by pulse width, basically, because it all comes from the sort of the radio control aeroplane market where everything was analog and you can specify things by pulse widths. But they are very effective and they're very good value for money, and I still think you know, they're a nice way to play around if you're building little tiny robots to use these technologies. It consists of a motor, of course. It's got a gearbox because, like I said before, we need to get the torque to a reasonable value to actually do something useful. It's got a position sensor in there as well, and it's even got generally a PID controller as well, so you can actually tell it the width, and it tries to get to the width that you've asked it for. These things are very, very good value for money. They're also going to be used in the 6 degree of freedom arms, which will normally be part of the robotics course. Another technology which is quite widespread and is used it's used certainly in robots, but also automated systems like CNC systems. They could be 3D printers or they could even be 3D milling machines, is the stepper motor. And the stepper motor is a very robust design. It's effectively a DC brushless motor, and the idea is you give it a pulse and it moves between two, if you like, stable positions. And these things, because of the way they're actually built, are capable of generating quite substantial torques without any gearing. However, they don't generally go around that quickly. And it's really used a lot as an open loop means of position control or angle control. They're very reliable as long as you don't overload them, and they last for ages. There's no things to wear out, there's no brushes to wear out, and as long as you don't burn it out, it should be fine. Really big robots, or even big systems for, you know, in civil engineering applications, use hydraulics. In fact, Tower Bridge in London, for example, used to use hydraulics until it was replaced by, I think it's now by motor drive. But the idea is you have a very, very high pressure source of hydraulic oil normally, which you use to push a piston backwards and forwards. And these are used a lot in these excavators for digging the road, and they can generate, you know, 10 tons of force on one of these actuators is nothing particularly unusual. So they're very, very powerful. The trouble with hydraulics is it's using oil, and oil is a terribly messy thing. These things are also potentially very dangerous, because if you get oil leaks at high pressure, they can be very, very serious. And even in applications where hydraulic cylinders are being used, they are slowly being replaced by electric actuation, because first of all, it's a much cleaner technology, and secondly, because the performance of electric actuation has gone up so much recently that it's kind of going to be winning in probably all fronts in the next few years. Another technology which uses pressurized gas in this type is the pneumatic cylinder, and these are quite nice for certain applications because they are very light in comparison with corresponding electric motors. They're slightly elasticy, as you'd expect. It's all quite compressive, and they're very, very clean. So you can use these for actuation for various tasks. Picking and letting go is a good one. They've got a very good response, and these are things because they're clean, they can be used in the food industry, and you wouldn't ever want probably a big dirty hydraulic system packing up some kind of food project in case you've got some spillages. And again, they're quite easy to control. You just basically have to control the flow of the air. And the force is limited by the air pressure, of course, so that is a limitation in this particular technology. Another take on using air, of course, is the air muscle. And the idea is you've got this cylinder covered with this woven kind of outer cloth. And when you blow air into it, the thing expands, and consequently the length of it goes down, right? So you can actually use this to pull with a quite significant force, actually. And it's kind of a little bit similar to the way, not human muscle is implemented, but kind of how it behaves in terms of, what a muscle will contract and expand out like this in the same kind of way. And they're used often in some soft robotic devices, and they're also used in things like the shadow hand, which has got quite a high number of degrees of freedom, and you can pack a lot of these little tiny air muscles into a relatively small space effectively, as you can actually see on this diagram here. If we want to start sensing things, then there's lots of different ways of doing this. Like I said, for a robotic arm, one of the important things would be to know the angle of the arm at the joints. Right, and one way of doing this is with an incremental encoder, and the idea is you're shining a little light normally through a slotted disc. It could also be a sinusoidally modulated one. There's lots of technologies, but the idea is you just calculate. You count the number of pulses going past, and you can have consequently an estimate of angle as this thing changes as it rotates. And they're very useful for positioning tasks. There's also magnetic versions now available, using newer technology, looking at the strength of rotating magnetic fields, and you can get very good performance from those as well. Another thing we are always quite interested in robotics is looking at how much force you're pushing, and the way to actually measure this is to use something called a force transducer. And basically, it's using a sort of Wheatstone bridge kind of arrangement, which is looking at how a resistance element changes as it gets strained. And in a nutshell, if you stretch something, it gets thinner, resistance goes up, and you can have an estimate of what the force was on the structure that it was actually stretched by. And here is an example of quite a substantial size force transducer. I think this is almost like 15 centimeters across, and the tiny little strips of some sort of silicon material are glued onto this big, strong element. And surprisingly, it may seem that you can actually measure the deflection of this element here, this steel element, on the basis of the change in resistance of these little tiny strain gauges, and give you a very good estimate of what the overall force is. In fact, this device itself is actually a 6 degree of freedom device, so it's measuring displacement in 3 directions and also rotation around 3 axes, or torques basically. Not to be ignored completely is sort of insight from how humans operate in terms of, how do our muscles work and how do we sense. So this is all quite interesting. One aspect of human, if you like, actuation is muscles can only contract So we can only have things which pull. They don't actually push back. You need, therefore, two muscles for each direction. For example, the biceps will pull your arm up and the triceps will pull it back down again. And very interestingly, within the muscles themselves, they have sensors for position and velocity, which then send information back, first of all via your spine, but also to your motor system. So they're very sophisticated mechanisms. It's also believed we get lots of information from skin stretch and maybe stuff happening at the tendons in terms of force as well. But I think there's a lot of insight to be gained by looking at the way, humans and also animals do actuation. We shouldn't just be thinking in terms of mechanical systems that we build ourselves. Finally then, control electronics is of course very important. So, and on this particular course you're going to be using things which control robots, of course. One way of controlling DC motors is, at the low level, is to use a DCH bridge. Basically, you've got to switch the direction of the current flowing through the motor. If you're using a stepper motor, you've got to somehow have some kind of controller which is going to generate the pulses and stuff like that. If you had a DC servo motor or just a DC brushless motor, you'll need the electronics to actually do that as well. And on top of all that, we need the overall controller implementing control strategies. It could be a state feedback controller as well. Thank you for your time.